9 Modern Agentic Design Patterns, your ultimate guide to AI agent architecture. Introduction, the evolution of AI agent design. Building AI agents, these 9 patterns are your ultimate shortcut to success. As AI agents evolve rapidly, understanding trending industry design patterns is key to staying ahead of the competition and building robust, scalable solutions. Today's AI landscape demands more than just basic chatbot functionality. Organizations need sophisticated agents that can reason, act, reflect, and collaborate to solve complex real-world problems. The patterns we're exploring represent the cutting edge of agentic AI design, each optimized for specific use cases and operational requirements. Let's dive deep into how each of these patterns actually works, when to use them, and what makes them powerful solutions for modern AI challenges. 1. Computer using agents, visual intelligence in action. How computer using agents work. Computer using agents represent a breakthrough in human-computer interaction, enabling AI to literally see and interact with user interfaces just like humans do. Step-by-step process. Query initiation. User sends a query through the web UI interface. Visual processing. VLM, visual language model, interprets both visual and text input within a secure sandbox environment. Reasoning phase. LLM processes the visual information and applies reasoning using available tools. Visual output. Results are showcased through the VLM back in the sandbox environment, creating a seamless visual feedback loop. Key technologies. VLM, visual language models, enable the agent to understand screenshots, UI elements, and visual contexts. Sandbox environment provides safe execution space for agent interactions. Tool integration allows the agent to interact with various software applications. Primary use cases: automated software testing and QA, customer support through screen sharing, software training and documentation, accessibility assistance for visually impaired users. Popular implementation: Operator, a sophisticated platform that enables agents to interact with computer interfaces through visual understanding and automated actions. 2. Codact agent, iterative code generation and execution. How Codact agents function. Codact agents embody the principle of thinking through action by generating, executing, and refining code iteratively until the desired outcome is achieved. Step-by-step process. Query analysis. User submits a coding request or problem statement. Action planning. Agent analyzes the request and formulates an initial action plan. Code generation. Agent generates code based on the plan approach. Environment execution. Generated code is sent to a secure execution environment. Outcome evaluation. Environment runs the code and returns results or error messages. Iterative refinement. Agent analyzes outcomes and refines the code until correct results are achieved. Key characteristics. Iterative problem solving. Continuously improves solutions based on execution feedback. Environment integration. Direct interaction with code execution environments. Error recovery. Automatically handles and learns from execution errors. Goal-oriented. Focuses on achieving specific outcomes rather than just generating code. Primary use cases: automated software development, bug fixing and code optimization, data analysis and visualization, API integration and testing. Popular implementation: Manus, a platform that specializes in iterative code generation with real-time execution feedback. 3. Self-reflection agents, quality through critique. How self-reflection agents operate. Self-reflection agents implement a sophisticated quality assurance mechanism through iterative self-evaluation and improvement. Step-by-step process. Initial generation. Main LLM generates a first draft response to the user query. Quality assessment. A specialized critique process evaluates the accuracy, completeness, and quality of the response. Memory integration. The system uses memory and available tools to identify areas for improvement. Iterative enhancement. Each iteration incorporates feedback to improve the response quality. Quality gate. Process continues until predetermined quality standards are met. Final output. Delivers the refined, high-quality response to the user. Key components. Main generator, primary LLM responsible for initial content creation. Critique system, specialized evaluation mechanism for quality assessment. Memory system, stores context and improvement patterns. Tool integration, leverages external tools for fact-checking and enhancement. Primary use cases: high-stakes content creation, technical documentation, research report compilation, creative writing with quality constraints. Popular implementation: OpenServe AI, provides frameworks for building self-improving AI systems with built-in reflection capabilities. 4. Voice agents, natural spoken interaction. How voice agents function. Voice agents create seamless spoken interactions by combining speech processing, contextual understanding, and natural response generation. Step-by-step process. Speech input. User speaks their query or request. Speech-to-text conversion. STT technology converts spoken words to text. Context retrieval. Embedding models and retrieval systems fetch relevant context and information. Agent processing. Core agent processes the request and plans an appropriate response. Text-to-speech output. TTS converts the agent's response back to natural speech. Natural interaction. User receives spoken response, enabling fluid conversation. Key technologies. STT, speech-to-text, converts audio input to processable text. Embedding models, create semantic representations for context matching. Vector databases, store and retrieve contextual information efficiently. TTS, text-to-speech, generates natural-sounding speech output. Primary use cases, customer service hotlines, voice assistants for smart homes, accessibility tools for hands-free interaction, automotive and IoT device integration. Popular implementation, DeepGram, provides advanced speech recognition and synthesis capabilities for building sophisticated voice agents. 5. Deep research agents, collaborative intelligence. How deep research agents work. Deep research agents orchestrate multiple specialized agents to conduct comprehensive research and analysis tasks. Step-by-step process. Query distribution. User query is sent to the main meta agent that serves as the orchestrator. Agent specialization. Meta agent identifies required expertise areas and assigns specialized sub-agents. Parallel research. Multiple specialized agents conduct research simultaneously in their respective domains. Information synthesis. Sub-agents gather information, store findings in shared memory. Result aggregation. All research results in memory are shared with an aggregator LLM. Unified compilation. Aggregator compiles diverse findings into a comprehensive and unified output. Quality assurance. Final review ensures completeness and accuracy across all research areas. Key architecture components. Meta agent, central orchestrator that manages the research process. Specialized subagents, domain-specific agents S-Agent 1 through S-Agent N. Shared memory, common knowledge base accessible to all agents. Aggregator LLM, synthesis engine that combines diverse research findings. Primary use cases, academic research and literature reviews, market analysis and competitive intelligence, legal research and case analysis, medical research and diagnosis support. Popular implementation, Claude Deep Research Advanced Research Orchestration Platform for multi-agent collaboration. 6. Agentic RAG, Enhanced Retrieval Augmented Generation. How agentic RAG systems operate. Agentic RAG combines the power of retrieval augmented generation with intelligent agent reasoning for more accurate and contextual responses. Step-by-step process. Query processing. User queries analyzed by the central agent. Multi-source retrieval. Agent orchestrates searches across external tools and vector databases simultaneously. Information gathering. Relevant information is retrieved from multiple sources, including APIs, databases, and knowledge bases. Context integration. Retrieved information is processed and contextualized by the agent. Generator LLM processing. A specialized generator LLM merges retrieval results with reasoning capabilities. Output synthesis. Final output combines retrieved facts with intelligent reasoning and analysis. Key components. Central agent orchestrates the entire RAG process. External tools. APIs, web search, and specialized databases. Vector database stores embeddings for semantic search. Generator LLM combines retrieval with reasoning for enhanced outputs. Primary use cases. Enterprise knowledge management. Customer support with real-time data access. Research assistance with fact verification. Educational content with current information. Popular implementation. Perplexity combines search capabilities with AI reasoning for accurate source-backed responses. 8. React agent. Reasoning and acting in cycles. How React agents function. React reasoning and acting agents implement a cyclical approach that alternates between thinking about problems and taking concrete actions to solve them. Step-by-step process. Initial reasoning. LLM1 performs the initial reasoning step using available context. Tool selection. Based on reasoning, the agent identifies and uses appropriate tools for required actions. Action execution. Selected tools are activated to gather information, perform calculations, or execute tasks. Result processing. LLM2 processes the results returned from tool execution. Iterative refinement. The cycle continues with additional reasoning and actions as needed. Final answer. Process concludes when the agent produces an accurate, complete final answer. Key characteristics. Cyclical processing alternates between thinking and acting. Tool integration. Seamlessly integrates external tools and APIs. Context awareness. Maintains context throughout the reasoning action cycles. Adaptive logic. Adjusts strategy based on intermediate results. Primary use cases. Complex problem solving requiring multiple steps. Data analysis with iterative exploration. Research tasks requiring fact verification. Mathematical and scientific computations. Popular implementation. Most AI agents. This pattern is so fundamental that it's implemented across most modern agent frameworks. 9. Coding agents, collaborative software development. How coding agents operate. Coding agents create a comprehensive software development environment through specialized agent collaboration and automated testing. Step-by-step process. Request analysis. User submits a coding request or development task. Agent orchestration. Main agent coordinates multiple specialized coding agents. Code generation. Dedicated code generation agent writes the initial code solution. Quality assurance. Debugger and testing tools work in parallel to identify issues. Iterative improvement. Code is refined through multiple debugging and testing cycles. Integration. Agents reference specialized development tools and frameworks. Outcome validation. Results are shared with the user and refined based on feedback. Continuous iteration. Process continues until expectations are fully met. Specialized agent roles. Code generation agent creates initial code solutions. Debugger agent identifies and fixes code issues.